questions on just administrative aspects of the course? Okay, good. So we're going to continue our sort of wide-ranging and sort of random assembly of pieces of information about introductory thermodynamics. So in order, roughly, we'll talk a little bit more about thermal expansion. You saw some demonstrations of this in Tuesday's class, so we'll try to be more quantitative. We're going to introduce the idea and to some extent reality of ideal gases, start to explore those. That'll be an important theme for the next couple of weeks. Briefly touch on temperature, since we haven't really talked about units, how we measure temperature yet. And then we'll probably spend maybe half an hour or so to the latter part of the class talking about thermal energy transfer, heat transfer, now we know it's thermal energy, and what that means in terms of responses of materials when we, let's say, add or take away thermal energy. What does it mean? Typically it means one of two things, maybe both things. It means that the temperature of that object, that material, will change. And it may stay within a particular phase. We already introduced briefly the idea of different phases, simply solid, liquid, and gas. So it may change temperature, staying within a particular phase, or if we are in a particular sort of area of phase space, it may actually change state or change phase. So we're going to explore what happens in those two scenarios, at which point we have a fairly good sort of macroscopic toolkit for understanding some basic problems in thermodynamics. So I hope I'm going to get through all of that. As you can see, there's a fair number of gadgets and demonstrations up front, so I think I'm actually going to start off with them, just to kind of get them out of the way. Let me take you back to the end of Tuesday's class. I showed you what happened when I applied a blowtorch to a long brass rod. Wasn't hugely dramatic, but you saw the setup, which had a brass rod pinned at one end, free at the other end, the free end being kind of pushed up against a lever, which was connected to a needle. And as I heated that brass rod, you eventually saw the needle deflect, which was an indication that in fact that brass rod was increasing in length. Okay? So that was one demonstration you saw at the end of Tuesday's class. And then just as we wrapped up, I took the same blowtorch and applied it to not a rod of brass, but to some thin strips, metallic. And what you saw in that case was a little bit more striking in that the metal strips tended to curl. So they didn't just change length, but they changed shape. So I asked you as a question to leave with on Tuesday, what do you think was happening in that second scenario with those thin metal strips? So what do you think was happening in that scenario with the thin metal strips?
I think one metal was expanding faster than the other one because its coefficient of thermal expansion was...
Okay, good. Yes, that's exactly what you were seeing. So rather than have a rod of a particular type of metal, brass in the first instance, those thin strips were actually made up of a sandwich, kind of two-ingredient sandwich, of two metals of different types and sort of glued together. And so what you were seeing there is in section something like this. Thin strip of one metal, thin strip of a second metal, again glued together. Let's say the lower one here has a tendency to expand more for a given input of thermal energy, a given temperature change, and the upper one, if this one is expanding more than this one and they're glued together, if you think about it, the only way that system can respond while keeping these two layers together is to actually curve. And so that's what you're seeing. It's an example of what's called a bimetal or bimetallic strip. And in fact, they're pretty commonly used, very simple gadgets. And I'm almost certain all of you know of one very common instance where these things are used. Anyone has seen such a bimetallic strip in use in a daily life application? Yes?
Is it in your thermostat?
It is in a thermostat. Many of you opened up a thermostat recently. If not, next time you see one, and nobody's going to get you into trouble for opening a thermostat, take a look inside. You will find a thinly coiled, it's actually already pre-coiled, bimetallic strip. It's pinned at the center, and it's kind of like a spiral going out from the center. as that bimetallic strip experiences different ambient temperatures, for example, the temperature in this room, which is pretty warm today, it does exactly this. It expands or contracts differentially depending on the two different metals, and therefore it coils or uncoils to different degrees depending on the temperature. If you set a simple contact, it could even be the arrow that you see on your thermostat. If you set a thermal metallic contact to the end of that spiral, you can imagine as it coils or uncoils, depending on the ambient temperature, the contact, the needle, will deflect to varying degrees, and it can either make or break an electrical circuit, which can turn on or turn off the heating in whatever room this thing sits in. So it's a very nice example of a use of an incredibly simple device, a bimetallic strip, relying on thermal expansion, contraction, to build a practical thermostat in your home, for example. Okay, so let's see what else have I got here. We're going to be talking about thermal energy transfer. And since we've already mentioned 3 common mechanisms for thermal energy transfer, I'm going to show you each of them, some more examples. They're kind of fun. So the first one I'm going to show you is conduction. Remember from Tuesday, conduction is defined by energy transfer where there's no bulk motion of the material in which the thermal energy finds itself. So there's no large-scale motion of the atoms or molecules of the material. And the energy is basically transferred by molecules vibrating increasingly rapidly, bumping against their neighbors and transferring energy from neighbor to neighbor. So this is pretty much exactly the same demonstration as you saw with the brass rod on Tuesday. It's slightly more informative in that I'm going to start heating it at the left end from your perspective. It's got 3 blocks suspended from this, and they're actually suspended by little blobs of wax. Wax, of course, is solid at room temperature, but as it warms, it changes phase and becomes liquid. So eventually, hopefully, this is kind of getting a little bit unexciting, there will be conductive thermal energy transfer along this metal rod. And it shows you the process from left to right, hopefully. Wow. Somebody's played a trick on me and made an insulating rod that brought in a thermally conducting one, which usually happens pretty quickly. Okay, there we go. So, thermal energy being transferred from left to right. And so, of course, it's getting warmer on the left end, and eventually that thermal energy is being transmitted by vibration along the rod. So I'm going to let the last one go. Okay, that is conduction as a means of thermal energy transfer, mostly in solids. It's of interest. We talked about convection as a second means of thermal energy transfer on Tuesday. In this case, again, it requires some medium, but also in this case, we expect, by contrast to that one, to have bulk motion of the material. Typically fluids. This is now a closed loop of water in a kind of rectangle. Got a little opening here that I'm going to put some food coloring in so you can sort of see this. So I've added some green food coloring sitting at the top. Good. So remember we talked about a radiator in a room and the effect of the radiator warming air and the circulation of air. Now I'm going to do pretty much the exact same thing but with water. I'm not going to heat this as much, otherwise it might explode. I'm going to heat the water at this bottom end here. Let's see if anything happens. It may take a little while. But I've heated the water here. And think about what we discussed with the airflow of the radiator in a room. Now I've heated the water at this point of this rectangle. It's presumably warmer here than it is everywhere else. One thing you know, though we haven't explicitly really talked about yet, is warm fluids are less dense than cold fluids. So here we expect warmer water to start rising. And if you think about it, since it's in a closed circuit, it's going to set up a circulatory loop, which is what you're starting to see now. Maybe you can see it against my blue shirt. You're starting to see the green food coloring circulate. Let's see, from your perspective, that's counterclockwise, right? So now you're seeing thermal energy transfer by convection. I'm just going to speed this up. It's been fine as it is. You can start to see the green food coloring come down here. So we've set up a convective thermal energy flow just by heating part of the fluid in this case. So conduction, convection. The third mechanism we introduced on Tuesday, which is something we're going to come back to primarily at the end of the semester, is energy transfer by radiation. Totally different mechanism and has much more to do with electromagnetism really than it does with thermodynamics, but just for completeness I'm going to show you now an illustration of energy transfer by radiation. So what you need to focus on are these two large concave mirrors. This one at its focus has a light bulb, which I'll turn on in just a moment. Concave mirror, we're not going to talk much about optics, but you already know to some extent what these mirrors do. They serve to focus incoming parallel light at a focal point, but conversely, if I have light at the focal point, you can think of this in the reverse sense. The light comes out here off this concave mirror, it's reflected as essentially an invisible beam of light. It meets its mirror image, bad pun, but it really is a mirror image over here. Another concave mirror, and its focus is a device called a radiometer, which is a surprisingly interesting and complicated gadget that you may have seen in executive toy shops or whatever. It's a thing with little blades on it. One side of the blades is colored black, the other side is shiny metal. And what you will see, hopefully, when I turn on this light source, is that we can transfer energy, really thermal energy perhaps, doesn't have to be, but it can be, via radiation. I don't know how well you guys can see this. You can't see it at all. But this thing is spinning like crazy. Okay, this little weather vane is spinning like crazy. And the reason it's spinning like crazy is it's collecting energy, invisible electromagnetic wave energy through here, coming back onto this, and it's making this little device spin. So those are three kind of fun examples of thermal energy transfer. Okay, having done that, let's get back to something quantitative. Let's talk a little bit more about thermal expansion. I do have one more demonstration that we'll talk about when we talk about ideal gases. Okay, so thermal expansion. Let me start writing some stuff up on the chalkboard. You've seen examples of it, primarily so far with that long brass rod on Tuesday and the slightly more complicated bimetallic strip. So let's see what we can quantify about this thermal expansion process. So we're going to begin in one dimension. There are a lot of obstacles to your sight lines here, so let's see if I can just get this one out of the way. Okay, so let's talk about thermal expansion. And this is something we're going to focus on primarily in solid and liquid phases for the time being. Let's look at a linear piece of material. So let's call this our linear system. So basically a long rod, just as we had with our chunk of brass on Tuesday. And let's say that this thing starts off with an initial length L, and it is at an initial temperature T. Okay? Again, we haven't yet introduced units for temperature, but we will in a few minutes. What we're going to find empirically, experimentally if you like, are a couple of very simple observations. So all we're going to do is measure the length of this material as the ambient temperature changes. And what we see are a couple of things. First off, we find that the change in length, delta L, turns out to a pretty good approximation, at least over a certain range of temperature, to be proportional to the change in temperature. Okay, so let's see. Some of you are having difficulty. Let me get this out of the way. Okay, so first thing we'll see is that the change in length, delta L, so this thing increases by a certain amount, delta L, is simply proportional to the change in temperature. And the second thing we see is that the change in length is actually proportional to the original length, L. Okay? So those are two empirical observations. You could measure those yourself based on a simple experiment, like our brass rod case. And essentially those are the two obvious things we find are sort of factors that change the length of this object. So we're going to combine these together, and no big surprise, this allows us to write that delta L, the change in length, is proportional to both L and delta T, combining those two observations. And as usual, as soon as we've got a simple proportionality behavior like this, our inclination is going to be to replace the proportional sign with an equal sign and a constant of proportionality. Okay, bad notation here, but the standard is to replace the proportional sign with a constant that has the symbol alpha. Okay? So, in fact, just to be super confusing, we typically write this. Okay? So, try not to be confused by this. This means proportional. This is just a constant alpha. And it is, in fact, the coefficient of linear expansion, for obvious reasons. And so we've already got now a very simple empirical relationship describing the change in length on the original length, dependent on the original length of our linear object, on the temperature change, and some coefficient of linear expansion. So if you like, I can recast this in slightly different terms. Delta L over L, the change of length, equals alpha delta T. Okay, so that's the fractional or proportional change of length. And I'm going to try and make this a little more tractable for you guys as well, because this is annoying. Okay, that works. And that's our simple parameterization of linear expansion of materials. Okay, so obviously if alpha is large, we're seeing large effects. If alpha is small, we're seeing small effects. I won't spend too much time going into detail of this. There are probably tables in our textbook that describe alpha coefficients for different materials. But just to give you a sort of rough sense of things, it's always good to have a rough idea of behaviors in physical materials. Something like maybe diamond, quartz, has a very low alpha coefficient, which means it doesn't change length. We're going to talk about volume size in just a moment. But it has a very low value of alpha. Maybe materials like steel, somewhat larger values of alpha. And it turns out certain solids, like ice, for example, have quite large alpha coefficients. But in all cases, these numbers are fairly small. So I'm going to write up just an order of magnitude. So these might be of order, I don't know, 10 to the minus 5 and 10 to the minus 4 for some particularly dependent materials. This is a small effect, right? Which is why you couldn't see that brass rod visibly changing length. That's good. If we had very large alpha coefficients in materials in daily life, life would be very different. It would be very hard to build objects that stayed rigid and stayed standing up if we had large alpha coefficients. Yeah.
Does this also apply to liquids, like this same equation?
Pretty much, yep. So you'll see here, this was really solids and liquids. Yeah, they tend to be a little bit larger for liquids, and probably you understand why. When we talk about liquids, the molecules, possibly atoms in liquids, they're already not locked in place. They're more, let me say, more dominated by thermal energy that's directly manifest in terms of the motion of the constituent atoms or molecules. But the behavior is roughly the same, but you'll see somewhat larger coefficients for liquids and solids typically. So this is a very simple parameterization of thermal expansion in a linear system. That's fine. But in general, we don't live in a world of one-dimensional objects, and it's much more common for us to be worried about, or interested in, I should say, about volume effects. So looking at three-dimensional systems, and now, okay, we need to get used to a new geometry of chalkboards in this room. It's going to take me a couple of sessions. Let me see if I can try and do this underneath in the same way. A little more space here. So in terms of a volume effect, so now rather than just looking at a one-dimensional linear system, I'm taking a three-dimensional object. Let's take it as being some sort of rectangular system, has a certain volume. And again, empirically, what we see just by looking at how things change depending on temperature and the original volume are the following observations. See in this case, very much the same as we have here. Change in volume is proportional to the change in temperature, and the change in volume is proportional to the initial volume, exactly the same in this sense. So I can write that the change in volume is proportional to G delta T, throwing in now a constant of proportionality. I'm going to say that the change in volume is, why not, let's call it beta, B delta T, and now I have a very simple parameterization of observed dependence of the change in volume of an object as the temperature changes. No surprise, this is a coefficient of volume expansion. Okay, so delta B over B equals beta delta T. Okay, completely straightforward extension from one dimension principle to two dimensions, not so interesting, but more commonly useful into three dimensions. So fairly straightforward. You can imagine there's a simple relationship between beta and alpha for a given material. I'm not going to work through this rather simple derivation, but of course in general, say that a volume is a length to the power 3, a length cubed. And so if I make use of this change in length for a linear system and do it to the power 3, there's a certain relationship that I get out of this, but in a certain, under sort of approximate conditions, I can say that beta is approximately equal to 3 times alpha. Okay, this is an approximation, but you can easily figure this out. And I'm going to just put a couple of lines of algebra in my notes for those of you who want to look at it. You can see to some good approximation that beta is roughly 3 times the alpha coefficient for certain materials. Okay? So that's pretty much all we're going to need to know about for thermal expansion of solids. And just to reiterate the answer to Joseph's question, also to liquids. And we may have to do simple calculations about changes in lengths or volumes of maybe slightly complicated systems involving solids and or liquids. I've put an example, a worked example in my notes, which I'm not going to do in class. I think it's not a good use of our time, but I'd like you to look at it. So take a look at the example in my notes. It's a fully worked example of volume expansion with temperature change. Just work through that. And then most likely I'll give you a couple of problems on a first PSET that will just exercise you a little bit in this thermal expansion topic. One thing I want to add before I pause and ask questions and then move on to talk about ideal gases. There's something slightly, possibly surprising about the behaviors of three-dimensional materials when it comes to the question of cavities or maybe holes in two-dimensional materials. And the behavior of the size of those cavities or holes in the thermal expansion. What do I mean more specifically? Take an example of maybe a ring. So two-dimensional object, roughly speaking, with a hole in the middle. If I take a ring and it has certain dimensions at room temperature, and then I change its temperature, let's say I heat the thing up. Here we've just talked about the sort of change in size of some particular material. A slightly surprising thing that I want you to be aware of is if I were to take that ring and increase its temperature, you might ask yourself, well, okay, let's say the ring is made of metal, the metal increases in volume, so I expect the outer diameter of that ring to increase. What happens to the inner diameter? Well, it turns out, and you can maybe think about why, it turns out that the inner diameter, which is to say the diameter of the hole, also increases. Okay? So it's that hole that's inside my metallic ring, as I warm the ring up, the hole itself increases in size, and then of course the ring as a whole increases in size. So the slightly surprising thing that is somewhat a source of confusion is that these holes or cavities in materials that are undergoing thermal expansion will, in most cases, depending on the materials involved, they will also increase in size, okay? There's absolutely no reason I can really think of why most of you would ever care about that stuff. Some of you might go on to be mechanical engineers, in which case it's clearly important, but just be aware of that. Otherwise, it's a very minor detail, okay? Okay, sort of questions on this quick phenomenology of thermal expansion. Yeah.
How do they deal with like sources of heating? Because I feel like it's very hard for you to have like to heat an object that's three-dimensional uniform.
Sure, absolutely. So, you know, in introphysics, we tend to make our life as idealized and simplified as possible. In practice, yeah, changing the, well, let me say, adding thermal energy to some object, you're usually applying it non-uniformly, right? I mean, you can be applying it at one end, as you saw with my rod there, or you could be applying it if you've got a sort of three-dimensional object. You can be changing the temperature of the environment, in which sense the energy transfer is coming from the outside in. We're not going to worry about the details of that gradient of thermal energy transfer. In general, we're pretty much going to assume that we can somehow uniformly apply thermal energy and that therefore there's a uniform temperature change. So we're going to only look at those simple cases. I think that's correct to say. Later on, and particularly for those of you who are, again, likely perhaps to be mechanical engineers, these things will have very real significance and importance, but for us, we're kind of looking at a much simpler idealized case. Another question before we turn our attention to ideal gases. Okay, so ideal gases. This was a little bit about thermal expansion of solids and liquids. Gases are a whole different category. Solids and liquids are much closer to each other than either of them are to gases. Just a reminder, I think we talked about this in the first semester when we talked about fluids and densities. In general, you'll find solids and liquids are within an order of magnitude density of each other, which means in all cases the molecules or atoms are pretty close to each other, so they're interacting strongly with each other. In gases, by contrast, the density is down by a factor of 1,000 typically compared to liquids. So of course our constituent atoms and molecules are way further apart in gases. And that's key for us in what we're about to talk about, and it'll carry over into the next couple of weeks. In the context of these things we call ideal gases, because the underlying assumption when we talk about one of these so-called ideal gases is that the constituent atoms and molecules are non-interacting. At least non-interacting in the sense that they have long duration forces between the atoms and molecules. It may be that the atoms or molecules collide with each other periodically, fairly rarely, but otherwise we're assuming non-interacting constituents for an ideal gas. So, let's talk about an ideal gas. First off, it's obviously a gas. So, low density. Atoms or molecules far apart. that they are non-interacting, except for occasional collisions. Okay. So in the early history of studies of heat and thermodynamics, people spent quite a bit of time observing, doing experiments on things that approximated these